Hey students, welcome to the second lecture of Linear Algebra 2. You see it's a new setup and I'm trying something new because I cannot record in my office anymore. So the idea is to use my iPad here and draw a little bit and then use parts of the overview notes to discuss. And you can also find on my homepage, besides these videos, you can also find these overview notes which contain all these theorems and propositions and so on. Then there will be handwritten lecture notes which are already online, which contain everything I write and also actually include more than this. And then there will be the video you're watching now, which is not online yet. And then of course you also see the homework. And on the bottom, for each week, you can also see which video and lecture notes you should watch. Okay, so let's try to start. So in this lecture we want to talk about linear maps, which we discussed last semester for the case of the vector space being the Rn. And before we do this, I want to recall a little bit what we did last time. So last time we defined what a vector space is, and a vector space was a set V together with two operations, addition and scalar multiplication, and these should satisfy certain properties. And since we will deal with different vector spaces at the same time, I also want to introduce some notation, which I also did in the tutorial notation. So a vector space is not just a set V, but it's a package of three things. It's the set V, some addition, and some scalar multiplication. So this tuple, this whole package, we call a vector space. And sometimes if we have different vector spaces, to really make sure that we know which addition and scalar multiplication we mean, we also write a small v on the bottom right. Okay, so with this, let's go directly to the definition of a linear map. So if I have two vector spaces, v and w, then a linear map is a function from v to w, which satisfies two conditions. And here using the new notation, so we have now two vector spaces, v with this addition and this scalar multiplication, and w which has this addition and this scalar multiplication. And then this first condition really means that f, when I have two elements in v, so these I add with the addition in v, and this should be the same as f of u, and f of u is an element in w, so this I need to add by the addition in w to f of v, and this should be the same for all u and v in v. And the second condition is the same statement for the scalar multiplication, that if I use the scalar multiplication in v of some vector u, then this should be the same as first applying f to u, which is an element in w, and then I can use the scalar multiplication in w. And this should also be the same for all u and lambda in R. Yes, so this we did for the case. So in linear algebra 1, we discussed this when, for example, v was the Rn and w was the Rm. And then we saw that a linear map from v to w is always given by multiplication by a matrix. So here I could take some element u and I send it to a times u, where in this case a was a matrix. So this I multiply with a vector of size n, so this needs to be an m times n matrix. But in the general setup, or maybe let's also say this a was also denoted, it was the matrix of this linear map f, and we saw every linear map between Rn and Rm can be written in a form like this. We always find a matrix such that the f of u is just given by multiplying with some matrix A. But in this general setup, this doesn't make sense because these objects we are considering can be really arbitrary objects like polynomials or matrices or maps. And there this multiplication with the matrix doesn't make sense. But what we will see today is that for a finitely generated vector space, this vector space is always so-called isomorphic to an Rn, and then we can describe arbitrary linear maps also by multiplying with matrices, which we will do in detail next time. Okay, so the next thing we want to define is what we also already did for the usual case, is the kernel and the image of a linear map. So if I have a linear map F from a vector space V to a vector space W, then the kernel of F is defined as all elements in V which get mapped to 0. And this 0 here, this is a neutral element in W. So let me draw a picture here. So this is V and this is W. So a map F goes from V to W, and in both of these vector spaces I have the neutral element 0, and the kernel are all elements here which gets mapped to this 0 here. So in general I can always have some element u, and u gets mapped to f of u, and all these u which gets mapped to 0, meaning f of u equals 0, this is the kernel of f. And the image of f are all elements in W such that there is some u in V such that W is given by f of u. So this means the image lives somewhere here on the right hand side, and these are all elements such that I can find some element u on the left hand side such that this element here is given by f of u. But of course not everything is in the image, not always. So for example here could be some element in W such that I cannot find an element in V such that f of this gives this element. So maybe let's give this guy here a name. Let's call it x. Oops. X. And here in this picture x is not in the image of f. Okay. So, and then with the same arguments as in the Rn case, both of these are, so this kernel is a subspace of V, so it's a subspace on the left hand side, and this image is a subspace in W. Okay. So now this kernel-image theorem, which we also saw, states that if the V is finitely generated and I have a map, a linear map from V to W, then the dimension of V is the sum of the dimension of the kernel plus the dimension of the image. Meaning in this image, in this picture here, the dimension of V is the dimension of the kernel plus the dimension of the image. So if the kernel is small or gets smaller, then the image gets bigger, and if the image is quite big, then the kernel is small. So for example, in the extreme case, if f is a zero map, so meaning that, so let's say I send everything to 0, so in this case the kernel of f is everything, so it's just v, and the image of f is just 0, because that's the only thing I can hit in W. And here you see that the dimension of v is just the dimension of the kernel, which is the same as the dimension of v, because the kernel is v, plus 0, because the dimension, this is the dimension of the 0 vector space. So this would be one extreme case, and the other extreme case would be that the kernel is actually just 0, which means, as we will see later, that the map is injective, and then the image of this map has the same dimension as the codomain, meaning the space V. So let me sketch the proof idea of this. So proof sketch, and you can find details in the handwritten lecture notes. So since V is finitely generated, then we know that also the kernel of f is finitely generated, because the kernel of f is a subspace, and we saw last time in proposition 111, I think, that if I have a subspace of a finitely generated vector space, then this subspace is also finitely generated. So in this case, this means the kernel of f is finitely generated. And finitely generated means that I can span the space by finitely many elements. In particular, the dimension is finite, so I can choose a basis for this space f. So let v1 up to vl be a basis of the kernel. So in other words, the dimension of the kernel is L. Then we know by what we did in the first lecture, by Theorem 1.8.3, that I can find more vectors such that these v together with these vectors give a basis for the whole space. So kernel of f is a subspace of v, and therefore this means that the basis of the kernel are linearly independent, and they are also elements in v, but I can find, so the statement is I can find elements u1 up to un such that if I take the basis elements of the kernel and I add these u's, that this is the basis of the whole space V. So this means the dimension of V is, well, the number of basis elements, which is L plus n. And we already saw L is the number of basis elements for the kernel. So this is the dimension of the kernel of f. And the number of u's here is n. So to prove this theorem, we want to show that this n is actually the dimension of the image. And what one can show then is that if I apply the f to these elements, u1 up to f un, then one can check that this is actually a basis of the image. And then we are done, because then we have a basis of the image with n elements, which mean that this n is actually the dimension of the image, which gives us the theorem. And how to do this you can see in the lecture notes. So you need to check that these elements are linearly independent and that they span the whole space. And this is actually not so hard to show. Okay, so let's do an example for these things. So first example, let me introduce this space Cn from R to R. So these are all maps or all functions from R to R, such that the nth derivative, which I denote by Fn, exists, and the nth derivative is continuous. And this, you can check, is a subspace to the space we called FRR, which were all functions from R to R. But of course, not every function from R to R, for every function there exists a derivative. So for example, for the function f of x equals the absolute value of x, here the derivative doesn't exist. Well, it exists everywhere except for in the point x equals 0. But this would be an element in f, but this is not in one of these n's. And this is defined as Cn's. This is defined for n greater or equal to 0. So the C0 is just the set of all continuous functions. And C1 are those where the first derivative exists and it's continuous, and so on. So now let's define a map. So define, which I want to call D, for taking the derivative. And this will be a map from Cn_RR. So first of all, this n needs to be greater or equal to 1. And this is a map to the space of all functions. And what I want to do is I send a f to its derivative. And this I can do because the n is greater or equal to 1. And in this space, Cn, the first derivative exists and gives a new function which is continuous. So in this case, one can check that this is actually linear. So D is linear, because you learn in calculus that if I take the derivative of a sum, it's just the sum of the derivatives. And also if I multiply some real number with a function and take the derivative, I don't really care about this number. So, but what is the image of this map? So if I start with a function where the nth derivative exists and I take the derivative, then I end up with a function where the nth minus 1 derivative exists. So this is exactly the image gives the Cn minus 1. So in the case when n is equal to 1, then I'm in the space of all functions where the first derivative exists and is continuous. And if I take the derivative, then I end up with a continuous function. And the kernel of this map is, well, we need to ask ourselves what gets mapped to 0 here. So the 0 function is a derivative of what? And the answer is it's a derivative of the constant function. Okay. So this is the first example. So in all these spaces here, they are not finitely generated. So we cannot really give an example for the theorem. But let's consider another example. So if I take the function f from the, for example, 2 by 3 matrices, we saw last time that this is also a vector space to, let's say, R3, where I, for example, send the matrix A, B, C, D, E, F to the vector A, D, E. So I just take this one, and this one, and write it into a vector. So this is linear, which is easy to check, because the addition for matrices is just defined component-wise, and also the addition for R3 is just component-wise, and then you can check that this is a linear map. And the image of this, well, what is the image? What can we obtain on this right-hand side? Because these A, B, A, D, and E are arbitrary, we can actually get everything here. So the image is everything, so F is surjective. And what is the kernel? So what gets mapped to 0 here? Well, every time A, D, and E are 0, we see that this gets mapped to 0, no matter what B, C, and F are. So, so what this is the span of this matrix, oh, not this matrix, and also not this matrix, sorry. So B can be arbitrary, C can be arbitrary, and F can be arbitrary. And therefore every linear combination of these three matrices, which we last time denoted by E12, E21, and this is E32. So these form a basis of the kernel, and the dimension of the kernel is therefore 3, and the dimension of the image is also 3. And we see here the dimension, this we had as an example last time, the dimension of the 2 by 3 matrices is 2 times 3. And this, in this case, actually is exactly the dimension of the kernel plus the dimension of the image, because both of them are 3. So this gives an example of this theorem here, that the dimension on the left hand side is given by the sum of the kernel. So the kernel is this is the subspace of the 2 by 3 matrices, plus the dimension of the image, which is the subspace of R3, but in this case it's actually everything. Okay, so now definition 2.4. So recall, we call the function f from an arbitrary set x to y invertible if there exists a map in the other direction from y to x, such that f composed with g is the identity y. So recall that this notation here means, so this is a function, and if I apply to something, this just means that I first apply g and then I apply f. So this is a composition of two functions, and the condition is that if I compose them, so if I now let me do it like this. So I have x and y here, and I have f here, and g in the other direction. So if I start in y, then go with g to x, and then go back with f, then here this should be the identity in y. So this shouldn't change anything. And also the other condition is if I start in x and go to y and then go back with g, this should also be the identity. So in other words, this here just means that fg of x, or maybe let's better call it y, is just y for all y in y, And again, this just means I apply G to Y, which is an element in X, and then I apply F, and this should be the same for all Y's, and also the other way around. And then we saw that a function is invertible if it's bijective, which means it's injective and surjective. So surjective means f can hit everything here, so the image of f is y. And injective means that not two different elements of x gets mapped to the same element in y. And now a new word. So if I have a linear map f, and this linear map is invertible, then we call this f an isomorphism between the vector space v and w. And if I have two vector spaces v and w, and there exists an isomorphism between them, then they are called isomorphic, and we have this notation that v is isomorphic to w, and we write this equal sign with this tilde on top. Okay. Yeah, so and this iso comes from the Greek word iso, which means equal, and morphism comes from the Greek word morphosis, which means to form, to shape. And isomorphism just means that they have, so if I have two vector spaces which are isomorphic, this means they have the same structure. So basically for us, as an object, as a vector space, they are equal. So for example, 2x3 matrices, which have 6 entries, are basically just the same as vectors of size 6. And this would be an easy example, as we will see later, that the 2x3 matrices as a vector space is isomorphic to the R6, the vectors of size 6. Okay, so now some statements on linear maps. So in this, the first statement is, if I have a linear map, then this is an isomorphism if, so if and only if the kernel of f is just the zero vector space, meaning f is injective, and the image is the whole space w, which just means f is surjective. And that injective is equivalent to kernel equals the zero space. So this we saw in linear algebra 1 in the homework. So this is linear algebra 1. This was on the homework sheet number 3, exercise 1. They showed exactly this statement here. So, and then the second statement is, if I have an isomorphism between two vector spaces, and I have a basis for the left-hand side, then if I apply the f to each of these basis elements and collect them, then the output is also a basis of w. And this follows also quite easily from the first one. So if I have a basis, this means these vectors are linearly independent. And then if I apply f, and f is injective, then this will also mean that f of these linearly independent vectors are linearly independent. And the other thing we need to check is if these elements span the whole space. But because f is surjective, and I can write every element in V as a linear combination of these b's, this also means that if I take linear combinations of these f of b's, span the whole space. And then as a consequence of number 2 is, if I finally generated vector spaces which are isomorphic, meaning there exists some isomorphism between them, then they have the same dimension. And since dimension just means the number of basis elements, this follows directly from number 2, because if I have a basis in V of n elements, then this f of b will also give me a basis of w of n elements, and therefore they both have dimension n. And then the fourth statement we also saw in the classical case, Namely, if I finally generate vector spaces of the same dimension, then to check if a linear map is an isomorphism, I don't need to check if it's surjective and injective. It's enough to just check if it's injective, meaning the kernel is 0, or if it's surjective, because one can show that these three statements are equivalent if the dimension is the same. And the proof is basically exactly the same as we did for the case when V and W are the Rn. Okay, so let's do an example. So, for example, the map F, which I said earlier, if I take matrices, for example 2 by 2 matrices, so A, B, C, D. So let's take the map or the function where I send A, B, C, D to the vector A, B, C, D. So it's not really an exciting map, but so this is an example for an isomorphism. Or for example, let's take G from R3 to P2. So in P2, remember this is polynomial functions of degree smaller or equal to 2, and R3 are vectors ABC, ABC, and this, for example, I can send to the function which sends x to ax squared plus bx plus c. And here you can check that these two are isomorphisms. Okay. So these spaces are all isomorphic. So if you, from the point of view of vector spaces, if you talk about polynomial functions of degree smaller or equal to 2, then it's the same as talking about vectors of size 3. So in the second example, the map D we had before, which was a map from CRR, so the functions where the nth derivative exists. Oops, so this is we saw the image is Cn minus 1. So I sent an f to its first derivative. So this is not an isomorphism. Well, why? Because what is the kernel of this map? Well, the kernel is not just 0, because we already saw that the kernel is given by the constant functions, and therefore this D is not injective. But in this case, this map D is surjective. Because here we said this W is Cn minus 1, and the image of this map D is exactly the space Cn minus 1. Okay, so now a new word and a proposition. Well, it's an old word, but in the new context. So if I have a vector space V and I choose a basis, which I denote by B, so I have basis elements B1 up to Bn, so in other words the dimension of V is n, then the coordinate map, which goes from Rn to V, is a map which sends the vector lambda 1 up to lambda n to this linear combination of these basis elements. And this, one can show, is an isomorphism which follows from the definition of a basis. So why is it injective? So CB is injective because these BI, they are a basis and therefore they are linearly independent. So the kernel of this map is just the 0 vector. So the only linear combination of these b's, which is 0, is just a linear combination where all entries of this vector are 0. And this map CB is also surjective because these b's are a basis and therefore they span the whole space. And the inverse map is exactly what we call this coordinate vector. So if I have an element in V and I have a basis B and I want to calculate the coordinate vector, this is exactly the inverse of this map, because the coordinate vectors gives me the linear the coefficients in the linear combination of this element written in terms of these basis elements. And here it's really important that everything here really depends on the choice of the basis B. So if I change the basis, then everything changes. Okay. So in other words, so this CB, if I have a basis, I get an isomorphism. This means if I have a vector space V and I fix a basis, I can see that this V is isomorphic to this Rn, and I get an explicit isomorphism. So every time we talk about V and we fix a basis, we can always talk about Rn. And this will be the step how we go from a linear map on an arbitrary vector space back to matrices. But going this step from V to Rn always depends on the choice of our basis. And if we change the basis, then these matrices will also change, as we will see next time. And the last thing I want to say is this corollary, which states that if V and W are finally generated, then these two statements are equivalent, namely that V and W are isomorphic, meaning there's an isomorphism, or the dimension of these are the same. And so the first to the second, this we already saw before. This was theorem 2.5 and number 3. Here's this one. If they are isomorphic, then they have the same dimension. But also the other way works. So if they have the same dimension, then we saw, so now how do we go from 2 to 1? So if V has dimension n, then it's isomorphic to Rn, but also W is isomorphic to Rn because it has the same dimension as V. And here, so if I have a basis, let's say I have a basis of V and I have a basis of W. They both have n elements because they both have dimension n. Then I can make an explicit isomorphism from V to W by first taking the inverse of the coordinate map with respect to the basis of V, and then here I can take the coordinate map for W. So in other words, I can take the composition of the inverse of the coordinate map and then I compose it with the coordinate map. And what this just means is so if I call this F, so F is an isomorphism, and for this you would need to check that if I compose two isomorphisms, then this is also again an isomorphism. And what this just does is, so F is a map from V to W, and V has a basis Vi, so if I have a linear combination, of these basis vectors. This is possible for all elements because this is a basis. Then this map just sends this to the same linear combination, but instead of vi I take the wi. And this is an explicit isomorphism after choosing a basis for v and w, and therefore if the dimension is the same, then these two spaces are isomorphic. Yes, and that's all for this lecture, and next time we will use this to talk about the matrices attached to linear maps for arbitrary vector spaces, and the step will always go like this, and we choose a basis for both vector spaces, and then both are isomorphic to some Rn and some Rm, and linear maps between Rn and Rm are just multiplication by matrices, and then we will say that this matrix is a matrix corresponding to this linear map after choosing two bases. See you then.